Hello, and welcome to Math with Usna. In this lesson, we're going to talk about triangle congruence using ASA, AAS, and HL. We are going to talk about these shortcuts for proofs. We'll talk about why they work, and then we'll practice some proofs. HL, ASA, and AAS are shortcuts to prove that triangles are congruent. Previously, we discussed SSS and SAS. So if you need a refresher on those, feel free to check that video out. HL is specific to right triangles. If you have two right triangles such that the hypotenuse of each triangle are congruent and the one leg of each triangle are congruent, then you can say that the triangles themselves are congruent. I'm going to go ahead and draw that out. Two right triangles. I show that they're right triangles with that box. I know that one pair of legs is congruent, and I know that the hypotenuse is congruent. That's enough to say that the triangles are congruent. I don't need to worry about the other angles, and I don't need to worry about that third side. The second one, angle side angle, that says if two angles and the included side are congruent, then the triangles are congruent. Okay, let's draw that out. Two triangles. We've got two sets of congruent angles and the included side. The included side is the side that is touching both of those angles. So this side here is included because it's touching both of those angles, and same thing over here. If you have this set up, two angles and the included side, you can immediately jump to say that the triangles are congruent. And the last one is AAS. That says two angles and the non-included side. What makes it different from ASA is the side that you pick. Two angles and the non-included side. Non-included means not this one, right? This is the included side because it's touching both angles. I want one that's not, and I want to separate out those congruents. Now, for AAS, you want to be careful with the leg itself. We picked this leg as congruent. Notice which angle it's touching here. It's touching the angle with that one line, that one tick mark. I want to make sure that I have the same thing set up on the other triangle. This tick mark matches with this angle congruence. It has to match up on the second triangle. That means I could not have that leg be congruent because it no longer matches up. Let's talk about why these even work. So I'm going to just start off by drawing a big triangle, and I'm going to make another one right on top of it. So I'll put that on top. All right, let's start with ASA. To have ASA, I need an angle, a side, and another angle. If I have two triangles such that this matches up, what I want to do is try to see if I can manipulate this triangle so that these remain congruent, but the other ones change. I'm going to grab this triangle and try to move it around. So if I were to move and change my triangle like that, so that it's still on that line, notice that now this angle is no longer congruent, right? One of them is clearly bigger than the other one. So the other two didn't change, but this angle definitely did. All right, what if I move it over here? So I'll put it over here. Now, this angle stayed the same. This side stayed the same, but this angle is clearly different. What if I move it inside the triangle? All right, now both of my angles changed, and that's not good. And if I take it outside my triangle, again, both of my angles changed. The only way to keep those three congruent statements congruent is to have this exact same triangle. So congruence, ASA, will always work. Let's do AAS. AAS uses two angles. I'm just going to do this one this time. And the non-included side, right? I'm going to do the same thing. I want to try to manipulate this triangle so that those two angle measures and that side stay the same, but everything else changes. If I try to put this there, okay, that didn't work. Clearly, my side got larger and my angle got larger, so that's not going to work. All right, let's try to put it this way. I put it over here. Again, the side's no longer the same length. The angle is not the same length. And if I do it over here, same issue, only now the side may be congruent, but the angles definitely are not. And no matter where I move this triangle, I'm never going to be able to keep that congruence true, where AAS is true, but the triangles are not congruent. It's never going to work. The only way this is going to work is if my triangles are congruent. So AAS is a congruence shortcut. The last one is HL. So for HL, I need 2 right triangles. So I'm going to make a big right triangle, and then I'm going to make another one right on top of it. I know that it's a right triangle because HL only works for right triangles. I'm going to have 1 pair of legs that are congruent and 1 hypotenuse that's congruent. I'm going to do the same thing. I'm going to try to move this triangle around so that those legs stay the same length, but nothing else changes, but everything else changes. If I make this larger, okay, now clearly my hypotenuse got bigger, so that's not helping. If I put this over here, now my hypotenuse is getting smaller. If I put it in the middle, now this is no longer a right triangle, which it has to be. This here has to remain a right triangle. Once I put this point up above into the triangle, it's no longer a right triangle. Same thing if I move it down here, this is now an obtuse triangle. The only way that this is going to work, if that those lengths remain the same, is if the triangles are congruent. So ASA, AAS, and HL are 3 valid shortcuts to prove that triangles are congruent. Let's do some examples. I'm going to go ahead and take a second to put in my statements here. So we have AM is parallel to GT, and I put my notation in the diagram. MT is parallel to GR, and again, put my notation in the diagram. And AT is congruent to TR. Okay, now I always want to start my proofs by looking at my given statements and trying to make conclusions. I've got a bunch of options for triangle congruence. I'm going to write them here. SAS and SSS, which we did before. We've just learned ASA and AAS and also HL. I'm probably not going to use HL here because I would first have to prove that the triangles are right triangles, and it's not likely that I would have to do that. So most likely we're not going to be using HL, so let's focus on the other ones. AM and GT. I know that parallel lines tell me something about angles. If I know that lines are parallel, I can make statements about angles. I have 2 sets of parallel lines, which means I am likely going to have 2 sets of angles. So I am going to guess SSS and SAS are not likely because I'm looking at ending up with 2 angles from those 2 parallel lines and 1 side. So it's either going to be ASA or AAS. If I know that AM and GT are parallel, then I know that A and GTR are congruent because those are corresponding angles. If you have a hard time seeing that, my recommendation is that you extend out those 2 lines and draw that transversal, and now it's a lot easier to see that those are corresponding angles. So if that helps you, go ahead and do that. Angle A is congruent to angle GTR. That is corresponding angles. I can also make 2 angles from MT and GR. If MT is parallel to GR and I have that same transversal, I can say those angles are corresponding. MTA is congruent to angle R. It's the same reason, corresponding angles postulate. This congruence, or this parallel line statement gave me this congruent statement. This parallel line statement gave me this congruent statement. I know I have 2 angles and a side, so definitely going to be using ASA or AAS. How do you know which one? You look at your diagram. I've got this side here, which is the included side. So 2 congruent angles and the included side, that is ASA. I'm going to say that the triangles are congruent. Triangle AMT is congruent to triangle TGR, and that is by angle, side, angle. So there is your proof for ASA. Let's try another one. I'm going to start off by putting my givens. CB is parallel to AD. CB is parallel to AD. There we go. And angle C is congruent to angle A. Angle C is congruent to angle A. All right, so once again, I like to just write out all my shortcuts here, just so that I have an idea of where I'm trying to go. Again, I'm not likely to use HL because I don't know that these are right triangles. So I'm going to cross that one out. It's probably not going to be it. Now I'm going to look at my given statements. What conclusions can I make if CB is parallel to AD? If you want to extend these out to make it easier to see, go for it. And I'm also going to extend my transversal. If those two lines are parallel, I can make a few statements. I'm going to say that CBD is congruent to BDA. And I can clearly see that those are alternate interior angles. Angle DBC is congruent to angle BDA, alternate interior angles theorem. Okay, so far I've got one angle congruent statement, and I've just proven another angle congruent statement, which means it's not going to be SSS or SAS because those require two sides, not two angles. So I am now looking to prove some side. I don't have any more givens left to work with. I've used all of my given statements. Now I'm going to go into my diagram. What can you notice in your diagram? BD is shared between those two triangles, and it's a non-included side. So I can say that BD is congruent to itself. How do I know that something is congruent to itself? That's reflexive property. Again, it seems kind of redundant to make that statement that something is congruent to itself. But remember, in proofs, you want to be very clear about your congruent statements. If I'm proving triangles are congruent by ASA or AAS, I want to clearly state two angle congruence and one side congruence. And the last thing I'm going to do is say that my triangles are congruent. Looking at my triangles, I can see that this side is not the included side, which means this is going to be AAS. All right, last example. I'm going to put my givens in here. HI is perpendicular to EG, and EH is congruent to HG. All right, well, if HI and EG are perpendicular, that means that I'm going to have a right angle here. Immediately, what should jump out at you is HL. You've got right triangles here. Always should try HL first. Let's go ahead and use our given statements to make conclusions. If HI is perpendicular to EG, what does that tell you? That tells you that angle EIH and angle HIG are right angles. That is the definition of perpendicular lines. I'm going to use that notation instead of writing out the word perpendicular. Okay, so they're right angles, which means that I have right triangles here. Okay, so now I'm pretty sure it's going to be HL because I have right triangles. Let me go ahead and put that notation in there. I also know that EH and HG are congruent. That was given to me. I should have put it in a little earlier. So I have that the hypotenuse for both triangles is congruent. I need to prove a leg. I have two options here. I could prove EI is congruent to IG, or I could prove HI is congruent to HI. This is the easier one to do, so let's do that one. IH is congruent to IH, and that should be a 2, not a 3, and that is by the reflexive property. So I've proven hypotenuses are congruent. I've proven the legs are congruent. I know that these are right triangles because I've stated that there are right angles. And that means I can just jump straight into my conclusion. Say EIH is congruent to triangle GIH. And that is by HL. And that's it. Those are all of your shortcuts for triangle congruence. If you learned something, please like and subscribe, and stay tuned for more videos.